welcome after post-lunch. I welcome for this second session. May I request Mr. Sudhanshu Pathak, Chairman of the session, former VP, Steel Making, Tata Steel, and also part of our group to check this chair. May I request Mr. Praveen Chaturvedi, Vice President, Tenava, please come to the dais. May I request Dr. Shomik Nag of Tata Steel? Yeah, he is here. And may I request Dr. Sham Mitra, IMNI, Issue Manganese Institute? Yeah, Sam is there. What I'll do, I requested Mr. Pathak that we are running little late, and therefore, if he, instead of 1 hour, if you could make it 45 minutes or 50 minutes, whatever it is possible on his part, it will be really nice. So therefore, what I'll do is, I'll tell very briefly about introduction of the year. While you people are settling down, I may mention Sudhanshu Pathak, superintendent from Tata Steel as a vice president steel making. He was responsible for steel making in Jamshedpur. He's a metallurgical engineer and joined Tata Steel in 1984. Subsequently completed PGDM XLI, and he also did Executive General Management CDEP in SID France. He has a long professional career. During 37 years, he did lot of changes in the one. With this small, he is also currently board member of many companies, and he is into the consulting. And I am happy to mention that he is also esteemed editorial board member of Steel Tech. With this small, I may request to kindly conduct. Thank you.
Thank you, Mr. Sen. I think good afternoon and welcome back. I think afternoon sessions are always a very difficult session. So, and on top of that, Mr. Sen has given us a target to finish this particular session in 50 minutes, which means the speakers who are on the dais, they'll also be under pressure to finish instead of the 20 minutes which was originally allocated, to finish maybe 15 minutes or so. I'm not sure we will have time for Q&A, so I can't escape by saying we'll discuss during lunch. So, but I do see that there is a tea and networking session. Maybe we can take those questions and have the discussions around that time. So to start with, we will, the first speaker in this session would be Mr. Praveen Chaturvedi, who is the Senior Vice President and heads Sales Upstream India, Tenava Technologies. He is a mechanical engineer from NIT Rourkela, and he's done his Master's Business Management from Symbiosis, Pune. He has had a long association with the steel industry of over 3 decades, working in Tenova for the last 13 years. Prior to that, he had been working in L&T, Ispat Industries, Dolvi, and Jindal Shadid, Man. There's a long list of his achievement, but time constraints, so I would simply mention that his working experience at Tenova since 2011 onwards, involved in upstream products, HYL, Energy-Ron, DRP, Pyromet, and melt shops business units of Tenova. Mr. Chaturvedi.
Thank you, sir. Good afternoon to all of you. So, the presentation topic of mine is about the pyrometallurgy. Before that, I'll take a few seconds just to, of course, this is confidentiality or disclaimer, we can say. We are part of the TechInt group. I'll take a few slides. Why I'm showing this? Because since we are talking about the sustainability, so to make you aware that we are part of the TechInt group, and here you will find there are 2 companies called Tenaris and Ternium. They are also the steel producer, and we are part of the same family. Last year's list is not yet declared by World Steel Association, but if you see the top steel producer, of course Tata Steel is there, but you will also find TechInt group, which is mentioned in the end. So we are part of the same family, like Tata Steel, we also make the steel. And more importantly, making steel is not a big thing, but the most important challenge is to become a sustainability champion, which was declared by the recently, I think last fortnight, by the World Steel Association, in which you can find the name of the Tata Steel also appearing here. And we are proud to be in the same family where our sister companies like Tenaris and Ternium, they are also featured. So that is more important. Now coming to the sustainable solution, yes, we provide the solution, sustainable solution in the metal and mining industries. And when we talk about the sustainability, of course, reduce cost, save energy, environmental impact, and the safety, and that is more important, improving the working condition. So the new mantra has been given by our management, sustainability. In between there is a new word has been inserted, Tenova. So that whatever product and technology we offer to our customer, it should be from the sustainability point of view. Of course, this is the slide which I am just sharing because it was already shown in 2017 in the same place by Steel Tech, in which we were already discussing about the polymer, green steel, hydrogen ready, and industry 4.0. And now this is the right time when we can implement it. At that time it was in conceptualization stage, but now we are really on the verge of implementing it. So sustainability, as you all know, we talk about the safety, energy efficiency, carbon footprint, technology, future challenges, which has been already addressed. Of course, there are many other challenges for the steel making, but flexibility also should be very important from the market and raw material. Those things already we discussed, so I am going to skip it out. And if you see in a broader prospects, we are into the iron and steel. We have got the hydrometallurgy. Hydrometallurgy I'll touch upon in the next slide. That also may be relevant to mainly the Tata Steel point of view. And then we are into the rolling, aluminum. Pyrometallurgy is the topic which I am going to cover in next few slides. Then of course we have got our metal handling division port facility. This is what, when I am talking about the hydrometallurgy, of course pyrometallurgy I will take in the next slide. So hydrometallurgy, we do the solvent extraction electrowinning, in which you can see the lithium processing we do. We do the lithium ion battery. More importantly, that you will see that we also do the nickel and cobalt extraction. Nickel and cobalt extraction. We already did an exercise here in Tata Steel when at that time we did an research and development here for the same. When Dr. C. Raghu Kumar was there, associated as a R&D for the, we did the feasibility study for nickel and cobalt. And yeah, we have the other divisions as well in the rare earth. But coming to the steel part, yes, we are into the DRI, we are into the reheating furnaces, electric arc furnaces, and these are about our product line. Coming to our Pyromet. Pyromet, we are a century-old company, just like Tata Steel. We have supplied more than 2,700 furnaces worldwide, having 100 years of experience. We supply AC and DC furnaces, which are used for the ferroalloys, platinum group metal, base metal, and alloy refining. And you can see in the ferroalloy sector, if we talk of, then we are into all the commodities, whether it is ferrochrome. We provide the technology as well, equipment for the ferroalloys like ferrochrome, ferromanganese, silicomanganese, even silicon metal, ferrosilicon. Those are the things. Base metal also, platinum, nickel, copper, platinum group metals. Ilmenite sand, yeah, that is also ilmenite, also TiO2. And then autocatalytic recycling. We are into iron and mineral wool. So from pyrometallurgy side, these are the activity which we do. And in the previous slide already we have discussed about the nickel and platinum, because those things can also be looked into, because right now we are importing it. So rather than that, we can also think of starting making it. Yeah, this is about our ferroalloys technology. We have supplied many furnaces for the ferrochrome. Some example are 33 MVA, 45 MVA, 66 MVA. These are the furnaces in ASA. In South Africa, we have supplied it. And also at other places like 75 MVA. These are for the ferrochrome. And international ferrometal, that is also in South Africa. We are basically, if you see, we are Italian-based company. Our head office is located in Italy, but the center of excellence for the Pyromet, that is ferroalloys, it comes from our South Africa, Johannesburg office. We are also into the silicon metal. So some of the references you can see, yes, silicon metal is also gaining momentum across the globe, and in India also a few players are really thinking on this aspects about the silicon. Yes, it is true that it is energy intensive equipment. You can see some of the references. We have already supplied 40 megawatt to silicon furnaces in Australia. Then also we are doing in US. Other division which we do is the platinum group metal and base metal. Some of the references I'm just touching upon. You can see also we have supplied to various places, including the auto catalytic converter, because as you know the scrap is getting vehicle are getting recycled due to the new policy which government has launched about the vehicle scrappage policy. So you will get a lot of also the catalytic converters that has to be recycled, and this is what we do at our Pyromet office. Of course, this is I'm just skimming it out. And then the same submerged arc furnace technology in the not in submerged arc mode, but in a brush arc mode, we can also make the mineral wool, not with the coal. So this is one of the way by which the sustainability can be thought of, replacing the coal cupola furnace which normally people make. We can go through the electric route making, just like submerged arc furnace, and we can make the mineral wool. So these are the things which can be also thought for the Indian context. Yeah, mineral wool we have supplied already across the globe. And the most important thing is the furnace information system that is nowadays mandatory in each and every process. So we as a Tenova, we design basically based on the iron ore, reductant, power and environment. So those are the things, and electricity rates, they are increasing. So basically we design based on those factors. How we design? By first principle, based on the mass and energy. Of course, China, they produce a lot of ferroalloys, but more important it is that they can supply the technology. They cannot supply the technology, they can only supply the equipment. But the more important thing that we design based on the whatever the input, what are the outputs, and what are the gases which are coming out. So these are the how we do design the mass and energy balance, and we come to the conclusion that what should be the optimum design of the furnace. Of course, these are some of the important things which are already in practice in our furnaces. You can see from reducing the electrical energy, there is MPH, there is multiple preheater, in which whatever gases are coming out of the furnace, from the submerged arc furnace, that is CO rich, and that can be used for preheating the raw material. Then dry gas cleaning system, that is also very, very important, very good thing in reducing the environmental impact. You can see we supply dry gas scrubber, multiple preheater, and that can also be applied to the DC furnaces. This is the multiple preheater which I was mentioning, that whatever we do, we recover the CO, which we have already implemented in Kazakhstan. And in the downside, you can see there is reduction in the power consumption, of course, and volatile metal in the reductant also get reduced. So and how we do the throughput also increases. So basically what we are doing, these are some of the closed furnaces, and from where we can extract the carbon monoxide, and those are used for preheating the raw material, so as to reduce the electrical consumption. Nowadays we are using the same philosophy for making the methanol, that ethanol, which can be used for the jet fuel and other applications. So this is a form of you can say a carbon capture, and storage as well as utilization. Yeah, this is the thing which I was mentioning, that yes, that carbon monoxide which we are able to tap, it can be used for preheating the material. So these are the technology. Then hot gas filtering. Yeah, it is a dry system in which no water is required, and that is very good from the environmental impact point of view. No water consumption, even 90% of reduction in the water consumption we can say, and it minimizes the load on the fumes. Yes, these are the baghouse system which we design. And then granulation, we were discussing in the previous session that what to do with the slag. Yeah, there are two systems. One is wet and dry. We generally nowadays follow the dry granulation system, in which we directly from the slag itself we do the atomization, and we remove the we break into a small particle, and those slags can be used for making the various applications like even for the road and paver block and other things which we discussed in the previous slide. Another aspect is to recover the thermal energy that is in making the steam, and then steam has various applications, waste heat recovery boiler which is already in practice, that also can be thought of. It also helps to reduce the carbon footprint about 10%. Then for the silicon metal production, we have got our own design of the electrode columns. This we call it composite electrode, which is generally beneficial for the silicon metal, and this is the one of the this is our patent design. And then there is an autofurn. Autofurn is a system which helps to basically control the furnace. This is the furnace controller. So it works in an auto mode. So there is no intervention of the human interface. So it can really work. So these are the all the parameters we can see, and it helps us to reduce the optimize the overall furnace operation. That is more important. And then ITAP, this is also the part of the same tracking, ladle tracking and furnace tap hole. So all the systems these are the part of our automation, and you can say machine learning and those aspects. This is the same pyro mobile. From the remote assistance also you can operate the furnace. So these are the add-on features. Any assistance is required, a person sitting at many thousand kilometers away can also operate the furnace, and they can also do the troubleshooting if any problem occurs. So these are the things which are already in the market. Robotics, of course, rather than using the human and not to compromise on the safety, these robotics are already developed for doing all the operation at the shop floor. And these are the digitalization. You can see also the monitor the furnace operation. You can see whatever the furnace erection activities can be also monitored. We can do the proper scheduling. We can do also the proper installation, which equipment has to come first. So we can do the monitoring of the project. I'm just skipping it off. And then yes, it is also one of the way by which we can replace the blast furnace, because these submerged arc furnaces, when it works in a brush arc mode, we can also use the low iron ore pellets, BF grade pellets, and we can use into the DRI. In a DRI, we also supply the DRI, and that DRI can be melted in such type of furnaces. We call it open slag bath furnace, through which the slag gets is taken out, and what we get is a pure metal, exactly similar to that of blast furnace. So it is a way by which blast furnace can be replaced with DRI and OSBF, open slag bath furnace. This is a type of DRI melter, and in the downstream the BOFs can be returned. The LD converters can be retained. So this is the you can see the same torpedo ladle can be used, and it can go into the. So no need of installing the electric arc furnace, because already BOF is existing. So it helps us for the gradual transformation or transition, you can say, from from blast furnace to DRI. And the same system is already implemented at China, because they want to retain their the BOF, that is LD converter, only to replace the blast furnace and coke oven. Like Bow Steel and HBIS, they have already implemented it. Then the other slag bath furnaces references, as I told you about the slag refining, that also we do for mineral wool. These are some of the installation. More importantly, yes, thanks to Tata Steel, and this was you might be hearing about the port. This is the one of the Netherlands, Imuddin, and this scheme was basically initiated by Dr. Samik Nag along with Dr. DB. We did, I think, many years ago, some 8 years ago, about how to do the DRI, and successfully it is now getting implemented at Imuddin, and this is for the Tata Steel Imuddin, in which our DRI plant along with the electric arc furnace is getting implemented. And another one is in Tata Steel, thanks to Tata Steel for giving us the opportunity to also install the electric arc furnace at Port Talbot. You might have heard the news, and the Tenova is involved in that by supplying that electric arc furnace. So these are the things by which we can move towards the reducing the carbon footprint and the sustainability aspects. I think you might be aware of the signing of that event, what happened. And yeah, when we talk about sustainability, so when we say Tenova in between, so it should come from the heart, not from the mind. So we should be ready for the next generation to be blessed with. So this is what power is. Thank you.
Thank you, Mr. Chaturvedi, and thank you for the presentation from Tenova. I think there are a lot of technologies which were presented briefly, or people can certainly engage with you to take it further. The other next speaker we have is Dr. Shamik Nag. He will be speaking on the latest development in blast furnaces and its future. Dr. Shamik Nag is currently the Chief of the Iron Making Research Group, R&D Division, Tata Steel. He has an enriching experience spanning about 24 years of blast furnace iron making, alternate iron making, and sustainable steel making. In line with what Dr. DB said, that all these conferences on sustainability, the speakers also who speak a lot and give out a lot of CO2. So I'll refrain from further. Shamik, I hope it's okay with you.
I'd rather save time till my laptop is getting set. So organizers have put a big clock here, which I can see, and they're continuously reminding me that time is crucial and we have to abide by the time. I'll try to save some time by skipping some of these slides or whatever it is. So this is the topic of my presentations, already told by sir. So we have already discussed this at length in the morning that blast furnace is the iron making, the steel making route. 70% of this is still through BF, DRI and other technologies, as Praveenji was telling, alternative options for blast furnace, but still it is yet to come in that big way, and we believe it will remain the most dominant iron making route for times to come. And here I am trying to show you how it has muted over time to remain as the working horse for the integrated steel plant, and what are the work going on to mitigate the challenges, environmental challenges, sustainability challenges of this process. And very briefly we'll cover the things around that, the research going on around that. So this I think this beautiful reactor was kind of invented sometimes in mid 1400s AD, has survived quite a long time, and now you can see this volume, really big in volume. Even 5,000 meter cube blast furnaces are not uncommon in India. Already Tata Steel has commissioned, few are also upcoming. So this remained the technology, and there are several things happened to make this technology viable over time and keep on improving itself. So if I try to collect all those things happened in this technology, this can be clubbed into 5 major baskets. Maybe I will skip some of those baskets for saving some time, but we can have a discussion off the stage as and when you want it. So these are the 5 major baskets on which technology interventions had happened and is happening. So one, of course, is how the things are. I think I have skipped a slide. No. So how the blast is getting preheated, and also how the material is being charged inside the furnace. Several things has happened. 1200 degrees centigrade hot blast temperature is not uncommon, rather common things, and BLT and very precise charging system where you can charge whatever you want inside the furnace in a very precise location is now a reality. So now on the major things has happened on the sensorization of the furnace. Many sensors got developed particular to the furnace, got adapted from different upcoming technologies, and then getting implemented. That has given a lot of insight into the process and thereby helping us to control the process better, and of course making it efficient, more fuel economic, etc. I'm not going into this individual sensors. just try to highlight two of the recent development in Tata Steel. One is this thermal imaging, which is giving us a kind of unprecedented insight into the blast furnace operation, just shown some real slipping happening inside the furnace. We can see that, and through certain image processing, we can also predict that before it is happening. So kind of a tool helping us to reduce the instability of the furnace. And also using these muon particles, we have developed a method to see the inside the furnace, so that the bottom part of the furnace, like hearth and area around the hearth, which is very hard to otherwise visualize, we are getting some insights and working on it to make it more visible and thereby help the operator to control it better. So not to mention several mathematical models backed up with all sorts of very powerful AIML algorithms is getting developed, which is kind of making blast furnace not only visible to the operators, but going ahead, it is making blast furnace smarter. Even the feedback system can be done, and then POSCO has kind of claimed that they have developed a smart furnace which they need very minimal otherwise interventions. So another aspects to extend the life of furnace. So from 10 years to 15 years, 15 years plus is now a present norms. So not to mention this Sumitomo's achievement of 27 years of life. So a lot has happened in the cooling system design and enhancement of the cooling systems and the lower part of the furnace, particularly for the hearth life and enhancement. Lot of material interventions and enhancement of the cooling, so that life has really improved. So, and lastly, on the injection systems, plenty has happened to make the coal available inside the furnace, and even 250 kg per ton of coal injection is not a kind of dream. It is happening every day in certain plants in Tata Steel. So plenty of things has happened. So I will not cover most of the things. If you have any queries, please feel free to ask me. So coming to taking cue from the today's discussion, most of the discussion is happening around the sustainability. Yes, blast furnace process as we stand alone, if we see it, it is a very CO2 intensive process because of its dependency on carbon. And there is a big question blast furnace is facing, how to make it less carbon intensive. So if we all know this, in the process of making hot metal, we make more CO2 than hot metal. But then how to make it more amenable to other reductants, particularly hydrogen or some green carbon, or can we do something to reduce this dependency on the carbon? Blast furnace process is very sensitive to the quality of the raw material. Iron ore quality, as we all know, is slowly getting deteriorated. So we have to make the process to keep the process economical and keep on the productivity things. We have to make it more amenable for to accept lower grade iron ore. And so I will show you one such solutions looking inside in the blast furnace process. Of course, plenty is happening on the beneficiation part of it. And of course, there are plenty of other technologies which are coming, which are kind of a different technology readiness level. Some are commercially available, are putting certain threats to blast furnace. So subsequent slide, I will show you how blast furnace can survive those challenges. So first, to make this iron making process in blast furnace less carbon intensive. So as we know that it is carbon which is the primary reductant here, can you get alternative fuels like say some green carbon from biochar or some biogenic carbon to utilize? It is possible. Can you use some hydrogen or hydrogen bearer gas, thereby reducing the dependency of carbon in the reduction process? This is the first gamut of things. Second, can you really, blast furnace gas which is coming out of the process is also very CO rich and having some amount of hydrogen. Can you in a way recirculate that gas so that the subsequent CO and hydrogen available in the gas can be further utilized? And third things, can you use the more PPR burden or some innovative burden to make the process more fuel economic, more efficient so that the less carbon is consumed? So I'll give some example of these things in the subsequent slides. So first with the alternative fuel and burden. So they are kind of independent levers. So both can happen together even. There are examples, good examples coming up in the world. I'll show you in the next slide. So if we can use some DRI or HBI or briquettes or some, say, I have not included here, some more reactive coke or some innovative additives to improve the combustibility of the coal, we can save some amount of carbon. So that can happen. Of course, it cannot replace 100% of the dependency of the carbon, but it has, I believe, 10 to 15% scope is still there. And on the alternative injections, I have already told about the biochar. Hydrogen bearers available within the steel plant also can be taken from other sources like natural gas or say hydrogen in different forms, can be injected and thereby can get rid of the carbon inside the furnace. But yes, there are inherent limitations of that. It is not a solution readily accepted, readily available, and we have to do a lot to make the process optimum for adapting these things. So here are some of the ongoing work, example of ongoing work. This is the example from course 50, where both the PPR burden and hydrogen bearer injections are adopted. And in experimental blast furnace, Nippon Steel has recently reported that up to 33 kg per ton of hydrogen they can inject. Of course, it is preheated by some means and at some temperature, and thereby can save 1/3 of the carbon dependency. So it will take some time to come into commercial scale, but it is something active research happening there, and solution will come. It will be sometimes from now. It is definitely coming up. So what in Tata Steel we are doing, like as I told, this recirculation of the gas. This is not a new concept. This top gas recirculation is a concept of early 2000, where ULCOS project has shown at piloting. ULCOS, in fact, successfully done the piloting in now swearing experimental furnace. Their 25% carbon dependency was reduced. So we are trying something little bit different from that. Instead of getting CO2 out from that, by putting some methane, we are doing some dry reforming and thereby regenerating that CO2 into syngas, into a combination of CO and hydrogen, and then again injecting that into the blast furnace. Here, and of course, introduction of some of the electrical interventions like plasma, or we will be preheating the gas, and basic calculation shows that we can go up to as low as 150 kg per ton of hot metal. Of course, this needs to be proved. We are doing in the detail engineering of this to try in one of our blast furnace at Jamshedpur. So other variant of this now at different scale of operation, like JFE is doing some small scale piloting by methanation of the gas coming out of the blast furnace top, and they are then subsequently injecting. Baus Steel has shown in their 450 meter cube blast furnace that they can do the classical top gas recirculation and successfully heating the gas and injecting it inside the furnace. By the way, the classical top gas recirculation technology at that point of time could not take the commercial scale implementation. One of the reason was this heating of the gas by some means, green heating of the gas by some means, but it is showing that now at scale solutions are available. So this top gas recirculation in some form will come, and this will dramatically reduce the dependency of the process on carbon. So for the raw material things, for the Indian context, we are very rich in alumina. Our ore is high with alumina. So other than the beneficiation and opting for alternative routes like Hisarna, we are also doing something inside the furnace. We have kind of discovered some additives which, when added to blast furnace slag, can really make the slag flow even at very high alumina percentage, as high as 25% alumina. So this is kind of giving us a solution to adopt very inferior quality iron ore in blast furnace and operate at a very high alumina. So solution now in use in Tata Steel. So this is my last slide. Hopefully I have saved some time. I don't know. So blast furnace, as I see that it is improving productivity, cost effective, and becoming sustainable. And there are competing technologies coming up, and many of the interventions happening there and the periphery will get adopted, and then subsequent, like say the process will be becoming more greener when the green electricity will come. I have shown example like heating of the gas by some electrical means will help us to get rid of some of the carbons. Say some amount of dry gas reforming at higher temperature can give us some solutions to get rid of the carbons. So thereby may not be the full solution within the blast furnace, but along with CCU, we'll be able to make the furnace as competitive as other alternative technologies are. Thank you.
Thank you, Dr. Shamik. And we do hope your last slide, blast furnaces will reinvent. I'm sure everyone's looking at that. So the next speaker in this session, and the final speaker, is Dr. Sam Mitra. He'll be speaking on importance of carbon footprint of manganese alloys from the International Manganese Institute. Dr. Sam Mitra is a graduate in mining engineering from the ISM Dhanbad. He completed his full-time MBA from IIM Kolkata in 1990 and joined Tata Steel, where he has had a long stint, and he further studied business administration at the Leeds University Business School. As a British Chevening Scholar, Sam later earned his PhD in minerals economics from the University of Dundee, Scotland, the UK. He's had a long stint at Tata Steel Limited and Tata International post his completion of tenure at the Tata organizations. He is moved into currently associated with the International Manganese Institute based out of Paris as the India representative and market analyst since January 2024. He continues to do his research and he's published his papers. Thank you. Dr. Sam Mitra.
Thank you, everybody. And I know I'm standing between you and the tea break. And of course, the tea is more interesting. So I'm trying to make my speech a little more interesting than the tea. Well, to begin with, a very small thing. The environmental footprint of the metals are not going to come down. I'm rushing through the slides because of the time issue. The circular economy model, whatever it does, at the best, can cut about 2/3 of the consumption, but 1/3 of production of metals will still have to come from primary production, which means you'll have to emit carbon monoxide. And why? One very crucial thing we must remember, that the metals, the abundant metals, all come in oxide form. Iron, manganese, titanium, you will only get in oxide form, not in sulfide. If we had sulfides, we wouldn't have been talking about CO2 emission at all. So unless and until we can look at pyrites or some other iron sulfur compound in the blast furnace, we will be talking about CO2. That's the beginning of, the Mother Earth has given us that particular kind of ore. Anyway, now coming back to this basic thing, we have had circular metallurgy talked about, but there's a new thought that reintegrative metallurgy, which is basically jigging manganese from your alloys, if I put it in very blunt terms. Or reintegrative metallurgy is also using the high carbon ferromanganese slag into your silicomanganese production. So the manganese industry has been knowing it, but they will have to probably step the gas on it. Now this is coming to the manganese industry, the emissions profile. You have the scope 1, which is the direct from your own operations. You have scope 2, which is indirect, but comes from the electricity that you purchase. So the thermal power that the India supplies gives you enough of scope 2 emission. Scope 3 is the broadest category, which includes all indirect emissions through the value chain, and this is where actually in the steel value chain manganese fits in. Now, what are the environmental footprints? There are various names, so I have just put the topmost one, the most important one in red. The global warming potential is coming from the greenhouse gas emissions, namely the CO2. There are other issues, the acidification potential, which can generate acid rain, the PM, the particulate matter, which of course has been talked about, the NOx and SOx emissions, and the POCP. POCP is the smog formation. These are also environmental hazards, but right now we are more bothered about the GWP, or the greenhouse gas emission component. Now what is this, as I mentioned, I represent the International Manganese Institute in India, and we have been conducting various life cycle analysis studies, which are basically meant to study the carbon footprint of the manganese alloys. The first one was in 2011. It started with 4 products, 10 sites, and 2 participants from India. The 2021, 8 products, 31 sites, no one from India participated. They were invited, but no one came forward. Sorry, I had put a timer, so the slides are running faster than I can. The 2024, we are expecting some members from IMNI members from India to join. These studies are free for the members. It gives an immense benchmarking opportunity. It also gives an opportunity for the member to know his own emission level, understand what is the global players are doing. And we also had a slag project for slag utilization. No one from India joined. Now, these are the measured footprints. The results that I am quoting here are from the IMNI initiated studies. Silicomanganese had 6.94 GWP. This is the carbon CO2 emission standard. It has come down to, in the 2021 second studies, scope 1 and 2 included, is 2.62. 3.5 is overall. High carbon ferromanganese is lower because the slag is being recycled and also because the energy consumption is lower. Now, where all the manganese alloy processes are impacting the carbon footprint? Furnace electricity, it makes it not just carbon footprint, but also in SOx, AP, POCP, the smog, the NOx, the PM everywhere. Then the furnace direct, the reductant uses, they are contributing. Then the smelter and other transport facilities, and mining makes a very big contribution in the West because of the overburden. So bringing that to the critical findings of the studies. Mines in the overall scheme of things are low impact, but they have high impact in PM emissions and waste because of the overburden, and that is directly linked to the mines stripping ratio and waste handling. One of the problems of India, at least as I knew in Sukinda, was the waste. I mean, there was a point of time when the Sukinda couldn't expand because they didn't have place to dump the waste, and the regulations in India, we know, will not allow you to dump the waste in any free land also. But anyway, smelters have the highest impact, energy and carbon proportionate to the ore purity and silicon. This is where high grade, if you notice in the last few years, China has gradually switched over to more of high grade burning. Reason is, if you burn high grade manganese ore, you will generate lower amount of emissions, slag. I mean, overall your footprint will come down. Low grade sinter, high silicon, it's going to burn, it's going to take more energy. SiO2, a total energy guzzler. Now optimize the furnace electricity and carbon requirements, optimize your ore burden also. Then link the operating parameters to the environmental impacts, because that's the only way you can make your strategic decisions in line with the environmental goals. And you have to coordinate the two sides so that the economic and the environmental performance goes together. They cannot be segregated anymore. Now the bad part, almost everyone knows about it, but I am highlighting the contribution. The bad is the highest contributor, the grid and on-site power. On-site power is a small fraction. Many producers are now switching over to solar power. I just read yesterday about JSL installing a huge solar unit in Odisha, Jajpur plant, so that they will not have requirement of on-site power from grid. But the grid also is a big contributor. So, and the good part which is already built into our system is internal recycling of the slag, getting the slag into construction material or any other useful diversion, and can you do the metal recovery? Here, I mean, almost every plant had seen at one point used to have a small jig at least somewhere, but the rate of recovery used to be so pathetic that you can probably do it for 20 years and still not clear your 1 year's metal dump. So, the tackling the culprits. Net effect will of course be the significant reduction in GWP and PM. These are the two main issues we can tackle here. One is increase the grid, the green fraction of the grid electricity. Why? Because India also has a lot of hydel power, which is naturally taken as green electricity. If your provider is giving you an agreement where he puts that, okay, this part of your requirement is going to come from hydel power, your footprint is going to go down. Install and run dust suppression as much to cut the particulate matter emissions. On-site electricity as far as possible, use the renewable sources, even go for electric driven vehicles within your premises. Utilization of waste not just in circular but also alternative uses, for reintegrative uses, for aggregate and other things where slags can be put into use. Those have to be pursued by individual plants on a much more aggressive basis. The CO gas utilization. This is an important area because in the closed furnace you get this option of utilizing this to use the heat and reduce your energy consumption. The quest has begun. The pioneering move by Eramet, I think in February 25, they have set a benchmark saying 1.9 is the CO2 level they are going to give in scope 1 and 2 in their manganese alloys across the board in all manganese alloys, especially medium carbon and low carbon included, compared to the global average of 3.9. This 3.9 is coming from CRU study based in 2023, and therefore this 3.9 is something which I don't take on face value. This is an average. And there are plants which are able to operate at 2.2 or 2.5 levels within our country. Now, where is Eramet scoring? Eramet is getting carbon-free power from the grid in Norway and France, and therefore they are able to give a very nice certification also along with the product, giving a blockchain-enabled tracing facility. Now, we have made available to our members and to outsiders also carbon calculators. You can do it yourself by going to the IMNI site and downloading the calculator. You can calculate your own carbon footprint and see where do you stand. Sorry to say not many people would do this, but it does address your pain points. Then you can obviously take strategic steps to reduce your on-site power emissions at least. Is it that difficult to tilt the balance? What are the devils? The devils are basically the diesel usage, the reductants, and the thermal power that we are buying. And of course the waste, slag and particulate matter being generated. Now, what are the good things we can do to control? One is, in the grid power you have alternatives. Another is on-site you go for green power as much as possible. And thirdly, you control your PM, you reuse your slag, you put slags to alternative uses. The green power grid, this is where the industry, the forum needs to wake up the government. Brazil has 90% generation from clean energy. So they're way ahead of us in this. EU at 71, China at 38, and we are at 22. And that too, our renewable figure has been stagnant for last 3 years. Nothing much has grown. We can't just stop at rooftop solar, we have to go much beyond that. And one more issue, our own thermal power plants are gas emitting units, and that emission is totally raking up havoc in our scope 2. You can see the India is at 708 compared to China, which had older plants but now sort of refurbished at 560. Japan is at 482 and world is at 473. Below this is Russia, I think around 450. So in target green, I presume no step is really small. The green energy, we are already seeing people taking interest. Bioreductant, we know about Tata Steel's trial and in ferroalloy, but I think it was in chrome, not in manganese. We also have, I just read about this research paper from one gentleman. He was talking about low carbon ferromanganese production, cutting down manganese, cutting down the energy requirement by almost 70% by using pre-reduced optimized manganese ore charge. This sort of researches have to be given industry support, and if industry can take it forward to the commercial usage, they benefit and researchers get the impetus to get into this sort of work. Our country has enough brains to produce this sort of new technologies. And lastly, I am coming to the roles that IMNI is playing in the community. I talked about the SLAG project, which is ongoing. The LCA Studies 3 has started. IMNI is providing active support to USA in their manganese interest group. It has a regular webinar series on regulatory affairs and on health, safety and environment, where finer things are discussed from the development around the globe. As I mentioned, it has a carbon footprint calculator to give guidance to the members about their own footprint. And also on the medical side, I'm told on the endocrine glands, manganese has a bad effect. So there are studies going on in that also. Yeah, I come to my last slide, hopefully quite within time. Yeah. So emissions control is no longer just a regional goal. It's not just CBAM or Japan or USA trying to talk about lower emissions. It's a global challenge, and India is facing this challenge at a very large scale. Not just steel, but manganese also achieve the standards to stay relevant. Because one more thing we should think about, if steel making becomes so difficult to stick to environmental standards, then maybe some other metal will take over. As simple as that. Nickel doesn't have that problem. Copper coming from sulfide ores do not have that problem. So think about it, maybe composites can take over. And India has an emerging steel powerhouse, and therefore a big manganese base needs to step forward, rather stay ahead in the game. And if we make concerted efforts, if we get right support from the grid power and everything that we are seeking from the government, probably it's not going to be too difficult to overcome the challenges. It actually needs optimal strategic planning and some support and a lot of enthusiasm from the producers. India is definitely aware of the climate control goals. 2047 or Tata Steel 2045 is not too far if we really look at the speed at which we are progressing. We are slow, but we need to walk this talk. And IMNI is a trusted partner in the journey, and we are ready to walk along. Thank you. For any questions, do mail us. These are references I've taken during the studies, and my email ID is there. And my colleague Dr. Agnieszka Leopold, she has been actively supporting me with the data and research from the HSC team. She is also there available for any questions that you can like to mail. Thank you, everybody.
I'm grateful to the speakers who stuck to their time, and I hope, Mr. Sen, we have complied to your targets. So thank you, Mr. Srivastava, Dr. Shamik, and Dr. Sam. Thank you.
I take this opportunity to thank Mr. Pathak for conducting it so well and finishing on time. Thank you very much for keeping our word, sir, because like what will happen the next one is that. Thank you very much all the speakers also. And may I now request our editorial board member, Mr. A.K. Sarkar. Mr. A.K. Sarkar, please come and do the honors to our speakers and the chairman. Please, a small token of appreciation from our end. We'll have individual board or we'll put it together at your side. Yeah, Dr. Shomik Nag from Mr. A.K. Sarkar. Yeah. We have a separate bag for carrying that plant. Yeah. Yeah, Dr. Sham Mitra is from IMNI, International Magnetic Institute. Mr. Praveen Srivastav, he's always there, to know about technology. He's associated with us right from the time we have started this He'll take this seminar. From 2009 onwards, one Dr. Amit Chatterjee was there. And 1 year to Mr. Pathak. Praveen Chaturvedi, yeah. He is there from our time we started in 2009. Yeah. Thank you very much. Thank you for correcting. Please come, we'll have a group photo together. Please come. We'll have a group photo together for the group. For this, please come, Mr. Sarkar. Yeah. Come. Come, you.